So I'm going to start putting the answers up here. So you can check depending on where you are. That's what my notes say. Do you think I'm wrong?
No, I just.
Oh, hard to read? Understandable. Go ahead.
I'm going to put a picture on for number 14, but what if you use, I use cosine to find FGY, so I got a different answer, but like when I use sine, I got your answer. Can you like,
Sure. Well, let's talk about number 14. Does everybody have their answers here? Okay. All right, so let's talk about number 14. So, a 50 kilogram steel cabinet is on the back of a dump truck. Just let me make sure. I am not muted. The bed is also made of steel and is slowly tilted. What is the size of the static friction force on the cabinet when the bed is tilted at 20 degrees? And then at what angle will the cabinet start to slide? Okay. So it's at some angle, which for the moment we'll call theta, but will be 20. Okay. So here's cabinet M. I've got a normal force that goes that way, a static friction force that goes that way, and my FG goes like that. And then I can have my components for my FG because that's going to be my X and my Y. So this will be FGX, this will be FGY, and that will be theta. Okay. Do you have that as theta?
Yeah.
Okay. Because I think that's an important thing. So the whole thing is, if it's the static friction force when theta is equal to 20 degrees, that means that the filing cabinet's not moving, so it's in equilibrium, which means that the acceleration in that x direction is equal to 0, right? So if I say F net in the x direction, that's going to be MAX, that's going to be 0. So in the x direction, I've got FGX and the static friction force. FGX is positive, static friction force is negative. FGX is equal to Fs. And from my diagram, if you have the same theta that I do, then FGX is FG sine 20 degrees.
Yeah, I have it. I must have just
Okay. No problem. Don't mind going through it.
Could you look at the second part too?
Sure. So now I want to know at what angle it's going to slide. So I can leave kind of my same picture there. But what I want to change is I want Fs to be Fs max. So in that situation, I know that Fs max is going to be mu s, which I looked up, times the normal force. And the normal force is going to be equal to mg cosine theta, right? Okay. So at the same time, I can still go back and do F naught x is equal to 0, because I'm at the point where if I tilt it any more, it's going to slide. Okay? So I've still got that my FGX is going to be minus Fs max. I'm skipping a couple steps there, but we know. Okay? So FGX is Fg sine theta, and that's going to be equal to Fs max, which is mg oh wait, I missed the mu right here, right? Thanks. So that's going to be mu mg cosine theta. So my Fg and my mg's are the same thing. And so basically I get mu is sine theta over cosine theta or tangent theta. So theta is equal to the inverse tangent of mu. Okay. Go ahead.
Why would F naught x have to be greater than 0? Because slide wouldn't.
Because you can't do that.
Oh,
So you can't answer that problem.
okay.
Okay.
You can't just say that in equality.
No, you can't answer that problem. So the thing to say is, if I'm using Fs max as my static friction force, then if I lift it up any more, if I make that angle any bigger, it's going to start to slide and I'm going to overcome.
Okay.
Okay. All right, we good? Okay, so did you have a chance to start the mechanics problem? All right, then let's talk about the answers to the mechanics problem. This is 2017 Mechanics 1. So an Atwood's machine consists of two blocks connected by a light string that passes over a frictionless pulley of negligible mass, as shown in the figure above. The masses are M1 and M2, but M2 is always greater than M1. On the dots below, which represent the blocks, draw and label the forces, not the components, that act on each dot. Each force must be represented with an angle, blah, blah, blah. So here's M1. So we're going to have what you could call FG1, or you could label it M1G. And then you're going to have a tension force. And you should be very careful. Actually, let's make this a little bit better here, because that tension force should be longer than your mg, or your M1G. okay, because you know what's going to happen to this system. You know that M2 is going to go down and M1 is going to go up because M2 has more mass. Okay, and I believe it tells you to use relative lengths of your arrows. So here's going to be M2, and again, you're going to have a tension force going up. Make sure that those two arrows have the same length because that tension has the same magnitude. Actually, yeah, because it's a frictionless pulley of negligible mass. So it is a pulley that we can ignore. Okay, so there's only one tension, but then since you know that M2 is going to go down, you need to make that arrow longer. And that is precisely why they put it on a grid, okay, so that you can make sure your arrows are the same lengths or longer. Questions about this?
It is
Fiona.
the line of FG2 is the longest.
Yes. So using the forces in the diagrams above, write an equation applying Newton's second law to each block. Use these equations to derive the acceleration and show it's given by that. You can look that up in your notes if you don't know how to do it, because we've done it and you did it in the lab. Okay, so I'm not going to do part B. All right, so the magnitude of the acceleration A was measured for different values of M1 and M2, and the data are shown below. Indicate which quantities would be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity. What do you think you're going to do? What are you going to graph? What's going to go on the vertical axis?
The acceleration on the vertical axis, and then the M2 minus M1 divided by M1 is M2 and M2.
Yeah, that's what I would do. Okay? Because they tell you you need to find a straight line, and because they tell you that the slope would give you the acceleration due to gravity. Okay? I added on my table a row that was M2 minus M1 all over M1 plus M2. Plot the data points for the quantities indicated in part C. Clearly scale and label all axes. Draw a straight line that represents the best fit to the data. Remember, you are not connecting the dots. You should have the same number of points above your line as you do below your line. In an ideal situation, your line would not go through any of your data points unless your data points were perfect, and they are not. Okay? So the whole point of a best fit line is you are taking all of the data into account and not favoring any of it. So those are things that you must take into account. Okay? And then using your straight line, determine an experimental value for G. My experimental value for G, which was the slope, was 10.7 meters per second squared. That's because that's how I drew my line. Okay. I tried to find points where my line actually either crossed the intersection of grid lines or went through like a halfway mark, so I didn't have to interpolate too much. But I didn't write down what the range is, but they always give you a range. Okay, so you don't have to get their answer precisely. Okay, but you need to have an answer that's within their acceptable range. Okay, questions on this one? All right. I'm surprised that's all there was to this one. Feels like there should have been a question like, oh, so your answers are smaller than G, justify that, but there isn't. Okay, your job for tomorrow is to do the forces homework. Tomorrow we will have class. Is tomorrow a remote day again, I think? So we will have class in Zoom and we will start energy. And just keep going and going and going and going and going until we run out of time. Okay? So you may go.